We're going to talk about constraints. And constraints is really a chapter 5 subject. We skipped it in chapter 5 and I put it here in chapter 6 because I think it makes pretty good sense as we talk about how constraints relate to rigid bodies and also to trusses. So here's just some information. It says equilibrium equations are necessary and sufficient to determine equilibrium. However, they may not be enough to resolve all of the reactions. For example, if you have a pin and a roller and a force coming off at an angle, we have two reactions, an AX and an AY. Because this is a roller, there's only a BY. Taking this into PX and PY, we can see that if we sum the moments about here, we can find BY. If we sum the forces in the Y, we can get the answer for BY. And if we sum the forces in the X, we can get AX. It's easy to see that the equations of equilibrium are enough to resolve all of the forces. However, if you have two pins, you have an AX and an AY, you have a BX and a BY, doing the same kind of process, turns out that there is no way to really properly resolve AX and BX. You end up with too many unknowns, and we call that statically indeterminate. Statically indeterminate means you can't figure it out with the rules of statics. You can determine that it is in equilibrium, but you can't figure out all of the components of the forces. So in other words, on rigid bodies, we must have a pin and a roller in order to determine the reactions when it's all connected together like that. A rigid body. Okay. Here's another example. Here you have a beam with a distributed force and two rollers and a pin. If I were to draw the free body diagram, I had AX and AY, I got a CY and a BY and that sort of thing. Summing the moments, I got a C and a B, and then some of the forces in the Y, I got C and a B, and some of the forces in the X, and end up having two equations. Yet so there's no forces in the X direction, but in the Y and the moment, I get C and B and an AY, and I have two equations, three unknowns, and there's no good way to resolve it. So in other words, this is illegal. Pin and two rollers doesn't work. If you have a gate often looks like it is two pins here, but in this case you have a same kind of situation where if you sum the moments about a point, you can't really, or you can get the BX, but if you sum the forces in the Y, it's hard to break up how much of the weight goes to each of the pins in the vertical direction. So it can't be resolved with two pins. Gates must be modeled as a pin and a roller, or a pin and a slot, if you will. So if you call this the pin and this is the roller, then there's no Y associated with down here, and that works. Or you could have this be the pin and this be some sort of a slot, where this takes the Y force and this only has an X force. This problem that we looked at before is a good example of how you would model this as a pin and a roller instead of something else. But the only good way to do this is to call this the pin and this have the BX and call that the roller. Call that AX and BX. Even though it's not really a pin and a roller, but that's kind of the way you have to model it. So there are a couple of errors, I guess, that can be made. If you have too few constraints, it becomes a dynamics problem. In other words, if you have something here with two rollers and you push a force on it, clearly it's moving in that direction. Some of the forces does not equal to zero, and that's too few constraints. If you have something with a pin here and some sort of a roller on the side here, it tends, and they've pushed down on it, it's going to tend to rotate. So there's nothing to resist the moment, and so that doesn't work. If you happen to have a pin here and a roller and you push the force up, then it's going to lift it off the it's going to tend to rotate. And so in other words, pins can't pull down. They can only push up, which means it can resist force this way if they're pushing up, but it can't pull down. And the other common support is having too many supports, and talked about this a little briefly. But supports that can be removed without destroying equilibrium are called redundant. And that means there are too many supports. For example, if you have a pin here and a pin here, and all these forces, you end up having too many unknowns, and that doesn't work. Same thing if you put this in a 2D kind of arrangement. If you have AX and AY, and up here you have CX and CY, you'd think you should be able to sum the moments and sum of the forces and resolve things, but if you just walk through it, you get 3 equations and 4 unknowns. In this case, one of these, AX here or CX, is redundant. In other words, one of these has to be a pin and the other one has to be a roller, or the other way around. So it's kind of curious. We have too many unknowns and when you have too many constraints. And this is back to the two-roller concept. And I just want to talk a little bit about mechanics of materials and bending and displacements and things like that, and try to just discuss a little why it works this way. So for example, if you had this pin, two rollers kind of thing, and what we said is that they each have a force pushing up, but you can't figure out how to distribute the forces. And think about this. Doesn't it make sense that the way that if this roller was separated by just a little bit, just say a very, very, very small amount, 1/1000th of an inch even, doesn't it make sense that it would be 0 unless there was some deflection? And if there was some deflection, which obviously we're not going to cover in this course, the amount of the deflection would determine the amount of the force that this has to support. So that's kind of the concept of the 3 equations, or the redundant supports. That's why you can't have them with statics. When we get to mechanics of materials, we'll figure that out. We'll figure out how to distribute the force over here and the force here and the force here, how to distribute it based on the type of bending, or based on the type of material, and based on how those forces are distributed. And then we can figure out, using mechanics of materials techniques, how to distribute those forces. But anyway, that's the reason why. Now for trusses, proper constraints need to have a pin and a roller most of the time. For example, if you have this truss and you have a pin and a roller, this is properly constrained. If this was a pin here, I'm going to draw a pin here and say, why is that not properly constrained for a truss? Well, what happens if this thing heats up? Again, this is a mechanics of materials question, but if it heats up, wouldn't you expect that there may be some thermal expansion and that sort of thing? And that would put force and stress on this pin that may not be acceptable. So for, again, reasons that are not only statically indeterminate, but for practical reasons, we would say that 2 pins are unacceptable in this configuration. But how about this one? Here, this one seems to be properly constrained. I got a pin here and a pin here. Why doesn't that one have the same value or the same concept? Well, think about this. If this was a roller, what would you do? If you push this thing, it would just slide right out. This whole thing would collapse. It'd fall over to the left, and it wouldn't be stable at all unless there was 2 pins supporting this structure. So what's the difference? Here's something you can look for. If between a pin and a roller there's a member, then you need a pin and a roller. If between this there is no member, then you need 2 pins. And logic will help you understand that. But let's look at this in just the other case. In this is in the vertical orientation, obviously, but this one can be the pin. This one has to be a pin as well because there's no member between us. Over here, this one is a pin. This one has to be a roller because there is a member between them. Okay, so anytime there's the 2 supports, if there's a member between them, then they have to be a pin and a roller. If there is no member between those 2 supports, then it's 2 pins. Now a little section out of another textbook might be helpful here, but anytime you have internal and external redundancy, we have this is for trusses now, we have an equation that actually helps us out. And I'll let you read this text. This is in your student notes, and so I'm not going to go through it at all, but there's an equation called Gruebler's equation that comes out of this, and it says that for proper constraint of a truss, you count the members plus the reaction forces, and that has to be equal to 2 times the number of joints for proper constraint. Members plus reaction forces is equal to 2 times the number of joints. If it's anything different than 2 times the number of joints, you have an unstable situation. So let's look at a couple of these things. If you counted the members and the joints here, let's go ahead and draw one of them together. I'll draw it on the first one here. There is a pin here, which means there are two reaction forces, and I have a pin over here and 2 reaction forces. If I were to count the members plus the reaction forces, I would say that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members plus reaction forces. Counting the joints, I get 1, 2, 3, 4, 5. I have, and then 2 times the number of joints, so that would be 2 times 5. And I would say that that is not equal. In other words, 11 does not equal 10. Therefore, this is a bad or not properly constrained structure. So what I'd like to do is walk through all these, the rest of these are printed again in your notes, and walk through all of them and see if you can find out which ones are bad and which ones are properly constrained, or improperly constrained and properly constrained. And then we'll go through these in just a few seconds. Okay, so here are the solutions for these. Again, I try to ask something like this on an exam, so it's to your benefit to understand how to use Gruebler's equation a little bit. But let's look at this next one. If I look at the reaction forces here, this is a pin, and this is a roller. So let's count the reaction forces plus the number of members. And I got this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's count the number of joints. That's actually going to be the same as it was before, but 1, 2, 3, 4, 5. So 10 is equal to 2 times 5. And so in this case, this is okay. This is properly constrained. And again, you can walk through all of those and get to the rest of them, and you can see that some of them are and some of them aren't.